So the very last type of reaction we'll look at for this chapter 4 section is an oxidation reduction reaction, often abbreviated redox reaction. So oxidation and reduction, or redox reaction, they are the type of reaction that involve electron transfer between species. So whenever a substance loses electrons or atoms, so whenever it loses an atom or an electron, it is said to be oxidized. And whenever it gains an atom or electron, it is said to be reduced. And so redox reactions are when or oxidation occurs when you lose atoms or electrons, and reduction occurs when you gain atoms or electrons. So a couple of mnemonic devices are oil rig. So oil rig, oxidation is loss of electrons, and rig, reduction, is gain. And another one, another mnemonic device, and you can pick whichever one works best for you. But this one's fun because it's got, I think that's Simba, right? No, not Simba. Who is that? Is that Mustafa? Ah, one of the Lion King guys. Anyway, Leo the Lion goes grr. So oxidation, loss of electrons, oxidation, gain of electrons, reduction. So Leo the Lion goes grr. So consider this equation down here. We have calcium solid plus 2H plus aqueous going to form calcium 2 plus and hydrogen gas. Now what's happening here? Consider this. Calcium solid has equal numbers of protons and electrons, right? Calcium 2 plus must have lost 2 electrons. Hydrogen, gaseous hydrogen has 2 electrons in that molecule. So molecular hydrogen's got 2 electrons, but these protons over here have 0 electrons. So what's happening is that 2 of the electrons are jumping off this calcium, going over and bonding to the hydrogen ions, and then those hydrogen ions are making covalent bonds and making this molecule, leaving the calcium ion oxidized. And notice that one of these things do not happen in a vacuum. You can't lose electrons to nothing, and you can't gain electrons from nothing. Right? It has to come from someplace and go to someplace, the electrons. So one more time, just so you have it up on the screen, the neutral calcium has lost 2 electrons and become calcium 2 plus. This is what's called oxidation. The calcium solid, the calcium metal, has been oxidized to calcium 2 plus ions. And again, the hydrogen ions have gained 2 electrons and have become this elemental hydrogen or molecular hydrogen. So in this case, the hydrogen has become reduced, and we call it reduction. Notice one thing cannot occur without the other. These two things have to happen at the same time. So one of the things that is very important with these redox reactions is what is called oxidation numbers, okay, or oxidation states. And they help us keep track of electrons during these chemical reactions because electrons are moved all over the place. But one of the important things about these oxidation numbers is they are not real charges, okay? They do not indicate, they might be the same as the charge on an ion, but they are not charges on atoms within the molecules themselves. All right, so keep that in mind as we're figuring out these oxidation numbers. So moving into a couple of rules for oxidation numbers. So for an atom in its elemental form, the oxidation, this is rule number 1, most important rule probably. The oxidation number is always 0. So going back to this last example here, since this is the elemental form for hydrogen, the oxidation number on those hydrogens would be 0. Okay? For any monatomic ion, the oxidation number equals the charge on that ion. So going back to our example again, this is a monatomic ion. oxidation number is equal to the charge on that ion, so this one would be +2. All right. So rule number 3, nonmetals usually have negative oxidation numbers. Okay, there are some exceptions to this, but in general, nonmetals have negative oxidation numbers. And the oxidation number of oxygen is usually 2 minus. Okay, so if you ever see an oxygen, think it's 2 minus. There's an exception though for peroxide ion. For the peroxide ion, the oxidation number is -1. So keep that exception in mind. So the oxidation number of hydrogen is +1 when bonded to a nonmetal and -1 when bonded to a metal. Okay, so the metal itself is obviously going to be the cation when bonded. So the hydrogen would have a -1 charge, but most of the time, or in other cases, when hydrogen is bonded to nonmetals, we call those hydrogens +1. Okay. The oxygen number of fluorine is -1. Okay. The oxidation number, not the oxygen number. The other halogens have oxidation numbers of -1 in most binary compounds, but fluorine will always be -1. And finally, the last rule is very much like the rule for formal charges. The sum of the oxidation numbers of all atoms in a substance equals the overall charge for that compound, whether it be an ion or a neutral compound. Remember that neutral compounds mean that the sum or the charge on that species is 0. Polyatomic ions, of course, the charge is not 0. It's equal to the charge on that particular ion. So finally, let's go ahead and use our rules to determine oxidation numbers and all of these things. So first off, we have this right here. And let's see if we can predict them. So this is nitrogen. It's nitrogen in its elemental form. So remember what the first rule is. Let's go back to it actually. For atoms in their elemental form, the oxidation number is always 0. So we're going to predict this one is 0. Notice we're determining the oxidation number of a single nitrogen in each atom. In this case, the oxidation number is going to have to be equal to the charge on that particular ion. Okay, so if all of these sodium ions are +1, that means that the nitrogen, in order to balance all of those sodium ions, needs to be 3 minus. So we're going to predict 3 minus here. Now fluorine, remember the oxidation for fluorine is always -1, and there are 3 of them in this compound, so that means that the charge on this nitrogen has to be +3, and so the oxidation number for that particular compound needs to be +3, because the overall charge on this needs to be 0. For this, remember that oxygen generally has a charge of 2 minus, but there are 3 of them in this compound here. So if there are 3 of these 2 minus things, that's overall -6 for all of the oxygens, and the species has a -1 charge. So if the species has a -1 charge, what plus -6 is equal to -1? That is +5, right? +5 minus 6 is -1, and so this nitrogen needs to be +5. Moving to this species, again, oxygen has a 2 minus charge generally, so each of these nitrogens has to have a +1 charge, right? 2 minus, each one contributes +1, but there are 2 of them, so the overall species is, non-charged. In this case, we have oxygen, which is a 2 minus charge, and nitrogen must have a 2 plus charge, or +2. Actually, let me write this down, +1. And over here, oxygen has a 2 minus charge, but there's a -1 overall, so 2 minus times 2 equals 4 minus. So if we have overall -1, what plus 4 minus is -1? Well, it's +3. So 4 minus +3 is equal to -1. So let's see if we got them. 0, -3, +3, +5, +1, 2, and +3. All right, so it looks like we're good all the way through. So go ahead and actually spend some time practicing determining oxidation numbers within the species. Either use your textbook example problems or some online example problems.